Hello everyone. Today in this video clip, I will continue conference chapter 16. I'll be talking about two sections today, section 16.5 and 16.6. On 16.5, we'll be talking about curve and divergence. So actually that section is a simple one, just formulas. And then the main thing is going to be on 16.6, we're talking about the vector function of a surface called parametric surface, and then we're going to use calculus to calculate the area of that surface. Okay, so let's start with 16.5. I'll be talking about curve and divergence. Okay, so say you have a vector function in 3D or 2D, as a matter. Say f equal to p MNOPQR. Okay, where P is a function of x, y, z, Q is a function of x, y, z, and R is a function of x, y, z. Okay, so we defined curve f. Curve vector f is defined this way. Let me show you the shortcut that I usually think of, and then I'll show you how to calculate. And then we have this notation called del, so from the gradient. Okay, cross f. This is cross from this is a vector cross another vector. And what do we mean by this? 3D, okay? So we cross, right? So I, J, K with three components of a vector in three-dimensional space. And we have gradient. Remember, let's talk about gradient. Say you got a function f. Then gradient f is what? df over dx, df over dy, partial derivative, okay? df over dz. So in here, gradient means that first of all you calculate partial derivative in terms of x, and then partial derivative in terms of y, and then partial derivative in terms of z. Okay, and this is for gradient. So this is three direction and two components I, J, K for x, y, and z direction. And gradient means partial derivative with respect to x, y, and z. And f is what? P, Q, R. That's what we have right here. And recall how we calculate the cross product of two vectors. First of all, for the I components, what? Partial derivative of R over dy minus partial derivative of Q over dz, partial derivative Q over dz. This is for the I components, okay? The I component. And then for the J components, what? dr over dx, or should be subtraction for the J, right? Minus dr over dx minus dr over dx right here, dp over dz. I'm going kind of fast in this because we learned in chapter 12, I think. Yeah. And then the last one is J, right? And then for the last component is K, dq dx, dq dx minus dp over dy. This is the J component, the K component. Sorry. Okay. So curve is a vector, really. You cross the gradient with the vector f, okay, and this is what we mean. This is just a shortcut. The formula the book gives you is right here. So by definition, curve f is a vector. Calculate this way. So in short, usually let me box this and make it stand out. In short, we usually write this, so it's easy to remember. Gradient cross the vector f. Okay. Gradient is something like this that we learned before. So gradient of f is a vector, what? df, dx, df, dy, df, dz. Okay, so with that, we have the formula. So let me give you guys an example of calculate curve of a function f. Example. Say I have a function f, a vector function f of x, y, z. Well, in full we should write that way, right? But later on eventually we becomes lazy. Just write F. That's good enough. Okay, equal to what? 2xy comma z squared comma 3yz. Just make up one example. Okay, so this is really my P right here. This is my Q, and this is my PQR. This is R. Okay, so I'm going to calculate curve of F. Based on the definition we just gave you, curve of F is really gradient cross F. It's del cross F, how you call it. It's like upside down delta. Okay? So, what you gonna do? I, J, K, 3 components, and then d over dx, d over dy, d over dz of 2xy, z squared, and 3yz. Okay, now I gotta, let me write down here. So I gotta do partial derivative for the I component, right? Partial derivative of this in terms of y, so d of this over y, right? So it's 3z, and then subtract partial derivative of z squared out of z is minus 2z. This is the I component. Okay, if I write I like that, then I gotta do add right here. Oh, actually, for the I, the j, so I do a subtraction. For the j component, what? 2xy dz is 0 because there's no z in here. Subtract 3yz dx is another 0 right here for the j component. So that's 0 really. And then for the last one, for the k component, z squared dx is 0, and then 2xy dy is minus 2x for the k component. Okay? And this is how the book writes. Usually I write this way, simplify. 3z minus 2z is just 1z, and of course 0 in the middle, and then this is negative 2x. You guys see that the answer is going to be a vector? So curve of F in here, and the answer is going to be z comma 0 comma negative 2x. It's really a vector. Okay, so that's the first part. Curve of a vector function is the cross product of gradient with a vector f. This is how you calculate it. Okay, and I'm pretty sure that you learned about cross product of vectors before, so it's just coming back. And I claim that in chapter 16 we're going to use this a lot. Okay, let's move on. There is one very important property that the curve going to give you. If curve of vector f is equal to 0, then you know that f is conservative. Remember what we mean by conservative? F conservative means that vector f is equal to the gradient of some function f, okay? For some function f. Okay. We have a function f. We take the gradient if vector function f right here equal to some gradient to a gradient of some function f, then we say that vector f is conservative. So with this term, you know that the curve of gradient f is always equal to 0. Right? Because this is already conservative, always, right? Hence, curve of 0. Okay. So this is the theorem, this is corollary. Okay, and I gave you example already. Now let me talk about the second part, talk about divergence. You see that curve, we talk about cross product, right? Of course, we can make a guess here. Divergent, where we're talking about the dot product. Divergent of F, divergence. Denoted by div, stands for divergent. Divergent of vector F, make a guess, it's going to be what? Gradient dot F. The previous one, curve, we do cross product, so divergence is going to be dot product, okay? So divergent is what? D over dx, comma, D over dy, comma, D over dz. I should use the bracket right here, and then dot with P, Q, R, and you know what we do for the dot product? This means what? dp over dx plus dq over dy plus dr over dz. Okay, so it's not too hard. So let me use the same example right here. So this is my function f, right? So I'm going to calculate the divergent of f. Divergent of f. Now it's going to be a function, not a vector anymore. Derivative, partial derivative of each of those in terms of x, y, z respective with, and then add them up. So 2xy dx is 2y plus z squared dy is 0, and then 3yz dz is 3y, and simply is equal to 5y. It's a function, not a vector anymore. This one, I got it from dp over dx, which is 2 derivative of 2xy over dx, which is 2y. Okay? And for the second one right here, dq over dy, which is the derivative of z squared over dy, which is 0. And the last one is dr over dz, which is the derivative of 3yz. This is my z, okay? Over dz, and that is 3y. You add them up, you have the answer. Okay? That's about the dot product. So pretty much that's about the first section that we're talking about today. Section 16.5, we are talking about two things, curve and divergence. And it really just gives you the recipe, the formula. All you have to do is follow the formula. You should have the answer. Okay, now at the end of this section of 16.5, we recall the Green theorem in vector form, and I'll show you, I'll rewrite a formula. Actually, I showed you guys this formula already. So, just have another look at it. Recall the Green theorem. The Green theorem say what? Say you have a vector f of pq. Oh, by the way, I'm always give you the vectors of 3 components, so p, q, and r. So if you got 2 components here, mean what? P, q, comma 0 for z, okay, for the third components, and then come back to 3. It's the same. Whatever, wait for 3, should wait for 2. Okay, if you got vector f equal to pr, and you want to integrate over that notation, over the region A on the xy plane, integral of vector f dot dr, that's how I wrote it, okay, which is integral of f is p, q, and then you dot with r is dr is d of x comma y, and the Green theorem say what? This is no more than integral of p dx plus q dy, and by Green theorem, this is going to be equal to single integral, right? Becomes double integral of dq over dx minus dp over dy over the region A. Okay? What was it called for the region? What was the name of it? I think it's A. Oh, region D. We'll call D. We'll call D. Region D. Okay. So Green theorem said this. They This is your x-axis, this is your y-axis, and this is your z-axis, right? And say you have a vector f, and you want to integrate vector f over a closed symbol curve. This looks like curve C, I think. So curve C right here. Counterclockwise curve C right here on the xy plane. Okay, whatever the vector f is, and this dr right here, r is the vector function of the curve C right here. Okay, so this is the r. Okay, vector r is going to give you a function of the closed curve on the xy plane. And then instead of calculating the integral of f on the curve, you can convert from single function of f on the curve to the double integral of dq over dx minus dv over dy on the interior area, okay, of the regions inside the curve. Okay? That's why we need the closed curve and symbol. Okay, that's green theorems tell you. From here, calculates right here. Okay. And actually in the book it just show you this form to this, but if you want to think of the vector, this is no more than vector f dot r. And why? What is it related? How is it related to the curve and divergence that we just learned? Okay. So if I think of it as p r comma 0, because we don't have the z component, so 0, right? So let's see how it's related to divergence. A curve in here. So you can calculate curve f. Curve f, which is gradient cross f, right? So we just learned it a minute ago. I, j, k, d over dx, d over dy, d over dz, and then pq0, pq0. Then let's calculate this. For the I components, what? 0, derivative 0 is 0, so dq over dz. Okay. For the I component, right? dq over dz. Should be a minus, I think, because this is 0 minus. So make sure that I got it right. dq over dz minus. Okay. And then for the j component, what? 0, derivative 0 is 0, and then minus dp over dz with not a minus become plus dp over dz. Okay. And then for the I component, for the j component, now for the k component, dq over dx minus dp over dy. Okay, that will be the curve of f. However, this is the two-dimensional vector function. So p here is a function of x comma y, and q here is also a function of x, y, so no z, or what? dq over dz is going to be equal to 0, because there's no z in here. Same thing here, 0. So really, this is 0, 0, and then dq over dx minus dp over dy. You guys see that quantity coming up? Or you can write this way if it's easier for you. This is the I component, the j component, this is the k component. So this is just what? dq over dx minus dp over dy, and everything times the k, right? All right. So, in short, that's curve f in two-dimensional space gonna be dq over dx minus dp over dy on the k component. Okay, k is the unit vector in the z component. This is k right here. Okay. All right. So if I got curve f dot k, curve is a vector, right? This is a vector. Dot k is meaning what? This thing right here. Curve f dot k is gonna be k is a vector. Means that this is another k right there, and then k dot k is 1 because this is your unit vector. Okay, and that's gonna be equal to dq over dx minus dp over dy. All right, so in terms of vector, the double integral of dq first, dq over dx minus dp over dy times dA is no more than double integral. This one is what? Curve f dot k dA. Okay? This is just an introduction. For later on, we're going to talk about something called the Stokes theorem, which is a more general case of the Green theorem. Why is that important? Let me redraw the picture right here. This is the x-axis, this is the y-axis, and this is the z-axis, right? The closed curve that you're talking about is, for now, for the Green theorem, is on the xy plane. It's flat, on a flat surface, flat curve, right? And then the interior region is going to be right here. And then the vector k is that way. Normal, unit normal vector, perpendicular to the region that you're talking about here. So the theorem say what? Integral of vector f dot dr. F here is a vector function times, this is a curve, okay? The line integral in terms of vector. It's going to be equal to curve f dot unit normal vector times dA, where A is the interior region of that surface. And later on, I will talk about this a little bit more ahead of time. Later on, the curve right here in the surface area may not be on the plane, could be this. This is a glow curve. Okay? How do I draw it? Okay? You guys see the surface? It's curvy. It's not flat anymore. And then k in normal vector can be represented as the general normal vector coming down. This is normal vector of a surface. Okay. And this is the closed curve we're talking about. May not be flat, may not be on a plane anymore. Could be any random closed simple curve. And we have a surface. And that formula is going to work. That's why they try to introduce you guys ahead of time. Okay. But for now, the main thing on 16.5 is the curve formula and divergent formula. You should get those two for me, that'd be good. But keep that, we're going to have something that's like curve f times the unit normal vector times the area. Okay. Now let's move on to the next section. I think let me double check on 16.5, see if I missed anything. Looks good. Okay. 16.6, I'll be talking about parametric surfaces and the areas. (16.6) parametric surfaces and the area. Okay, so let's start with the parametric function for a surface in a three-dimensional space. Let's use vector r, two variables. Okay, so uv. As the book used uv, so I use uv. It's defined this way. It's x in terms of uv, y in terms of uv, and z in terms of uv. Recall that we have a curve. If you have a curve r, then it's going to be a function of one parametric variable. Okay, two variables, you're going to have a surface. So, say This represents something like this. Okay, so you have a surface. This is a curve, all right? Could be close to, may not be close to, the surface. Okay. The y-axis, the z-axis. I'm sorry, the x-axis, and z-axis. Vector function uv represent this. Okay. It's a point on the curve. Gonna be vector r uv. Okay. I think I should give you an example. You see it. How about r uv equal to 2uv comma u squared minus v squared comma u plus v. And what do we mean by this? Means what? X is equal to 2uv, x is a function of uv, y is equal to u squared minus v squared, and then z is equal to u plus v. So if you want to find a point on that surface, okay, 0, 0. So r 0, 0 is equal to, means what? If u equals to 0, v equals 0, keep in mind that u and v are parametric variables, okay? So it's not on that zy plane. This is what? 0, 2 times 0, 0 is 0, 0 squared minus 0 squared 0, and 0 plus 0 is 0. So this is really the origin. X 0, y 0, z 0. Try another one. How about r 0, 1? So u now is 0 and v is 1. It's going to be 0, 0 squared minus 1 squared is negative 1. And then 0 minus 1 is negative 1 again. Try another one. R of, say, 1, 1. 2 times 1 is 2. 1 squared minus 1 squared is 0. 1 plus 1 is 2. You see? So plug in the value for u and v. You're going to calculate x, y, z is going to be the 3 components of the vectors. And together, we have all the points going to give you a parametric surface, a surface using the parametric form. Okay. Now let's try to relate this to something that you guys actually learned already in Calc 2, I think. Recall in Calc 2 you learned the surface area of revolution, I think. Let me try to record it back. So you got the x-axis right here, the y-axis right here. I'm talking about Calc 2, right? So we don't have 3D yet. So you have a function right here. This is f of x. Okay? And recall that we're going to rotate the f of x function around the x-axis, for example, or the y-axis. Let's talk about x right here. You are rotating the function around the x-axis. Okay? And then they ask you to calculate the surface area of that revolution. Okay? And I claim that this has now become a very specific case of this general formulas that we have for the surface area. So let me try to represent that thing in the 3D. Okay? Now 3D, so how about draw it this way? I want you guys to imagine that this is my y-axis. This is my z-axis, and my x-axis is coming out. Okay, the x-axis coming out of the board, and the point, and you are rotating about the x-axis. If you look at this, we're going to be like this. Okay, x-axis coming out right here, and the tube you are rotating about the x-axis. Okay, y-axis right here, x-axis right here, rotating about the x-axis. And how do you find a point on that surface when you're rotating about the x-axis? Really rotating, this is the radius r right here, this is angle theta right here. Okay, the x-axis, so any point on the x